Well, hello there. Welcome back. We're going to continue our quest of maxes and mins and derivatives by looking at a function and using the second derivative test to determine if there's a minimum or a maximum at a value where there's a horizontal tangent, aka a critical number, but not where it's undefined. So let's just look over to the right at the criteria for using the second derivative test. Let's say that f prime of c is equal to 0. If the second derivative happens to be positive at that value, we have a local minimum at c. And if the second derivative is negative at that value, then we have a local maximum at c. So we need to first find the critical numbers where the first derivative is equal to 0, and then use those in the second derivative. So here we have our function, and it does require a product rule to find the derivative. So I'm going to say x is the first, and e to the negative 0.5x is the second. So the derivative, as we know with the product rule, is the derivative of the first, which is 1, times the second, which is e to the negative 0.5x, plus the first, x, times the derivative of the second. Now the derivative of an exponential is e to the negative 0.5x times negative 0.5. It's itself times the derivative of the exponent, the inside. So I'm going to clean things up, and all that means is I'm not going to write the 1, and then I'm going to say minus 0.5x e to the negative 0.5x. And actually what I'm going to do is, before I say it's simplified, I am going to factor out e to the negative 0.5x. And that's going to leave me with 1 minus 0.5x. So this is my first derivative. So I want to know where that's equal to 0, so I set it equal to 0. So if we need point of reference here, this is finding critical numbers. And remember that since it's in factored form, we know that each factor could be 0. Now remember, an exponential never takes on a value of 0 because there is no exponent that creates 0. So this is no solution. And on the right, if we add 0.5x to both sides and divide by 0.5, we have x equals 2. So x equals 2 is the critical number we're going to pay attention to. Now we move to the second derivative. So using the equation in the box, we're just going to use the product rule once again. So f double prime is, so the derivative of the first, which is e to the negative 0.5x, the derivative of that is e to the negative 0.5x times negative 0.5, and then times the second, which is 1 minus 0.5x, plus the first, e to the negative 0.5x, times the derivative of the second, which is 0 minus 0.5. The derivative of 1 is 0, the derivative of 0.5x is 0.5. Now at that point, we could simplify, but remember, we are just going to be substituting a value in to see what the second derivative is. So I'm going to leave it as is and just substitute 2. And we have a lot of 0.5s and 2s here. So let's just remember, let's just look at this here. So 0.5 times 2 is 1. So this is e to the negative 1 times negative 0.5 times, well, this is 1. That makes it look like a fraction though. There we go. So that's 1 minus 1, so that's 0, so that whole term drops out. And then we have minus 0.5 e to the negative 1. So this whole term goes away, and we have negative 0.5 times 1 over e. Now remember, e is a positive number, so this whole thing is negative. Therefore, there is a maximum, a local maximum at x equals 2 by the second derivative test. What is the value of f at that point? Well, remember, the maximum value would then be f of 2 equals, now remember, f of x was x e to the negative 0.5x, so that'd be 2e to the negative 0.5 times 2, which is 2 times e to the negative 1, which is 2 over e. So the local maximum point occurs at 2, 2 over e. And I have a graph here just to confirm our results. Here is the graph of y equals x e to the negative 0.5x. And as you can see, the maximum point turns out to be a global max at x equals 2, and 0.736 is the decimal approximation of 1 over e. So there we have it. Another way to find mins and maxes is to use a second derivative test.